All right, how did that go? Did you have at least a little bit of fun? Maybe you can see how you can make this fun for your students. Let's have another look at this together. Okay, so here's the website again, and I've cleared the initial pattern that you see when you load it. You've had a look at the explanation here. So 4 very simple rules essentially that determine this game of life, and the idea here is really that the yellow cells in this case are alive and the gray cells are dead, and then depending on the number of cells and where they are that are alive, something happens in the next iteration. In particular, if a particular cell has 1 or no neighbors, it dies. If it has 4 or more neighbors, it also dies, so kind of simulating loneliness and overpopulation. But each cell with 3 neighbors survives, and more importantly and more interestingly, each cell with 3 neighbors becomes populated. So this is the only way essentially how we can create new cells, or how the simulation creates new cells after the initial layout that we have provided. If there are 3 live cells neighboring one particular cell, we're creating 1 more. This illustration is slightly misleading because, of course, the 3 neighboring alive cells still remain in that iteration, and then in the next iteration, again, depending on these rules, we will see that some of these may die, new cells may spring up elsewhere, etc., etc. We can essentially iterate that. If you played around with this a little bit, as I will do now, so let me try a bunch of different things here. Very simple pattern to start with. What does that look like? That doesn't look like anything. Nothing happens in this particular case because, let me pause this here, none of the cells surrounding any of these cells have 3 cells as neighbors, so we're not creating any new ones. But each one of these 4 cells here has exactly 3 neighbors. So it doesn't die out because of overpopulation or because of loneliness. Everything stays exactly as it is. Okay, we can make this slightly more interesting here. For example, by doing something like this. Okay, it seems that we have kind of reached a stable state again. This doesn't change for exactly the same reason as I've mentioned before. So these cells in the middle here now actually have too many neighbors, and that's why they don't come alive. And the cells outside don't have enough neighbors, similar for the ones that are here. Okay, let me reset and clear this, and if you've played around with this, you will have seen that, of course, we can make any kind of pattern here. These don't have to be squares or symmetric or anything. This could be something weird like this, and depending on what you're doing here, let me make something that's a little bit larger than that. This can, when you start the simulation, actually look quite interesting. We do a couple more things here. Start, where things kind of move around, and over a number of iterations they change, and then until eventually they stop, as in this case here. Or, let me try to do this here. We get an oscillating pattern as we have seen before, or we could get something like this that kind of continues to move and continues to grow and then shrink again and grow and shrink again until in the bottom down there it has reached a stable state, so we're not changing this anymore. But now we're changing it again. Okay, now I need to scroll a bit. So you can get these quite intricate simulations here where things happen for quite a large number of iterations, so that this has now, you can see this in the bottom right, has more than 100 iterations for this particular pattern that I started with, and we still see things changing. Of course, the longer we run this, the more we will eventually see at least parts of this become stable, as we see, for example, here for this square and this square here and this square here. And then we have this oscillating pattern here. That's kind of interesting. We also have these down here, and these kind of just happen by themselves, right? We didn't create these patterns to start with. They kind of just appeared. Okay, now this is growing even more, so let me zoom out a little bit so we can see what's going on in other parts of this space. As you can see, in this particular case, more and more parts of our simulation space here becomes stable or oscillating, and we have only these relatively small parts that keep changing, and oh, one of them has disappeared now, and the other one, oh no. So kind of interesting, right? Very nice to play around with this, and also something that you can show to a student and say, hey, interesting patterns happening here. Of course, again, so I can play around with this while it's running, as I'm sure you have done as well, and kind of do something about these very boring, stable patterns here and get things moving again. And as you can see, it's still going, this part over here, so this can really run for quite a long time. Okay, let me stop this here. I hope that you had some fun with this and that you have a somewhat better understanding now of what Conway's Game of Life is, and hopefully also some ideas on how you might take that back into the classroom. That's everything for now. We will come back to this in a bit, and then we'll dive a little bit more into how this relates to computer science and the other and more sophisticated things that we might be able to do with it.